Okay, so here's a scenario I want you to think about for a second. You're sitting in a train. The train is moving at 60 kilometers per hour toward the east. You get up, walk toward the front of the train, and you're walking at about 5 kilometers per hour relative to the seats around you. Now, how fast are you moving? Well, it depends on who you ask. To someone sitting in the train seat watching you walk by, you're moving at 5 kilometers per hour. Easy. But to someone standing on the platform outside watching the train go past, you're moving at 65 kilometers per hour toward the east because they see you being carried by the train at 60 kilometers per hour plus your walking speed on top of that. Both of those people are correct. They're just measuring from different positions. So what is a reference frame? A reference frame is just a coordinate system that a particular observer uses to measure motion. Think of it this way. When you define a coordinate system, you pick a direction for positive, you pick where the origin is, and you make all your measurements from there. That coordinate system belongs to you as the observer. It's anchored to you. Now, if another observer is moving relative to you, they're carrying their own coordinate system. Their origin might be shifting, their positive direction might be pointing somewhere different from yours. Same physical event, two different sets of numbers. This is what your physics textbook means when it says, the choice of reference frame will determine the direction and magnitude of quantities measured by an observer in that frame. And that's a genuinely important statement. It's not saying the physics is different. It's saying the numbers you measure are different. Same reality, different descriptions. So let's make this concrete. Here's the classic scenario, and I love this one. Why might it seem like you are moving backward when a car passes you on the highway? You're on the highway. You're driving at 100 kilometers per hour. A truck comes up behind you and passes you at 120 kilometers per hour. So you need to imagine a little here. From your frame, the frame attached to your car, that truck starts behind you and moves forward past you. Its velocity, as you measure it, is 20 kilometers per hour in the forward direction. Makes sense. But now think about what the truck driver sees. They're in their frame. They see you moving backward relative to them at 20 kilometers per hour. To the truck driver, you appear to be moving in reverse, even though you're both going forward relative to the road. Same physical situation, two completely consistent descriptions. Neither is wrong. This is genuine physics. Velocity is not a property of an object by itself. Velocity is always a measurement between an object and a particular observer's frame. Now, every single problem you've ever solved in kinematics has been assuming you were measuring from the ground, from a frame that's stationary relative to Earth. You just never had to think about it because everyone agreed on the same frame. The moment we introduce a second observer moving relative to the first, we have to be careful. The numbers will be different. The signs might flip. What looks like forward motion in one frame might look like backward motion in another. So what you need to be able to do is identify the reference frame of a given observer and recognize that measurements of velocity, the direction, the magnitude, everything, are specific to that frame. So students sometimes write, the velocity of the object is x meters per second, without specifying relative to what. That's an incomplete statement. Velocity always implies a reference frame even when the problem doesn't explicitly say so. If nothing is stated, you can assume the ground frame, but know that you're making that choice. And it's not just velocity. Position coordinates are also frame dependent. If you're in a moving train and you place a ball at a certain position in the aisle, the position of that ball in the ground frame is changing every second, even though in your train frame, the ball hasn't moved. What this means is when you switch from one reference frame to another, position measurements, velocity measurements, they all transform. This means measurements from a given reference frame may be converted to measurements from another reference frame. Now, I want to take this idea and make it quantitative. How do you actually calculate the velocity of something in one reference frame if you know it in another? The velocity addition rule. Imagine this setup. You're standing on a train platform. You're in the ground frame. Let's call it frame G. A train moves past you at 20 meters per second to the right, which I'll call the positive direction. Call the train's frame T. A person on that train throws a ball forward relative to the train at 5 meters per second. What is the velocity of the ball as you measure it from the platform? Intuition says 25 meters per second to the right, and that intuition is exactly right. You add the velocity of the object in the train frame to the velocity of the train itself in the ground frame. Let's write this symbolically. I'm going to use a clean notation. V ball relative to ground equals V ball relative to train plus V train relative to ground. Or in shorthand, V B slash G equals V B slash T plus V T slash G. Here, B is the ball, T is the train, G is the ground. The velocity of B relative to G equals the velocity of B relative to T plus the velocity of T relative to G. Just to make this formula stick in your head, imagine this T in the denominator canceling with this T in the numerator, and what you get is VB slash G. Of course, this is just a notation. There's no numerator or denominator as such. That is, the observed velocity of an object results from the combination of the object's velocity and the velocity of the observer's reference frame, and combining them involves the addition or subtraction of vectors. So let's work through the directions carefully. Here's where students make errors. The direction matters, and the sign of each velocity is determined by your chosen coordinate system. Let's set up clearly. Positive direction is to the right. Example 1. Train moves right at 20 meters per second, ball thrown right forward at 5 meters per second relative to the train. VB slash G equals VB slash T plus VT slash G equals positive 5 plus positive 20 equals positive 25 meters per second. Ball moves at 25 meters per second to the right relative to the ground. Makes sense. Example 2. Same train moving right at 20 meters per second. Now the person throws the ball backward toward the rear of the train at 5 meters per second relative to the train. VB slash T is now negative 5 meters per second. Backward is negative in our coordinate system. VB slash G equals negative 5 plus positive 20 equals positive 15 meters per second. The ball still moves to the right relative to the ground. It's just moving slower than the train. The train carries the ball forward even though the ball is moving backward relative to the train. Example 3. Person walks backward toward the rear of the train at 5 meters per second relative to the train. As seen from the ground, what is their velocity? VP slash G equals VP slash T plus VT slash G equals negative 5 plus positive 20 equals positive 15 meters per second to the right. Still positive, still moving right relative to the ground. The train is faster than their backward walking. The most common mistake students make here is ignoring the direction of the train's motion and just adding magnitudes. Always assign signs based on your coordinate system before doing any arithmetic. A student who writes velocity equals 5 plus 20 equals 25 meters per second when the person is walking backward has made a critical error. Now, what about subtracting? Sometimes the question asks you to find the velocity of object A relative to object B, where both are moving. This is like the car passing you on the highway situation. You're driving at positive 80 kilometers per hour to the right, and another car passes you at positive 95 kilometers per hour to the right. What is the velocity of the other car relative to you? So let us say you are in car A and the other is car B. Then using the earlier equation, we can modify it for this situation to write, and how you should read this equation is VB slash G is the velocity of B relative to the ground. VB slash A is the velocity of B relative to object A. And VA slash G is the velocity of A relative to the ground. And remember, this is an equation, so you can move terms left and right. Then, using this equation, we can say VB slash A equals VB slash G minus VA slash G equals positive 95 minus positive 80 equals positive 15 kilometers per hour. The other car is moving at 15 kilometers per hour forward relative to you, which matches your intuition that it slowly overtakes you. Now, flip it. What are you relative to the other car? That is VA slash B. So we can modify this equation, that is VB slash G equals VB slash A plus VA slash G, as VB slash G equals negative VA slash B plus VA slash G. And you see we flipped A and B here, but also reversed the sign here. And it makes complete sense, since that is to find the velocity of A relative to B. You just flip the perspective. If A sees B moving at positive 15 kilometers per hour, B must see A moving at negative 15 kilometers per hour. VA slash B equals negative VB slash A. It is a direct mirror image. Therefore, VA slash B equals VA slash G minus VB slash G equals positive 80 minus positive 95 equals negative 15 kilometers per hour. You appear to be moving backward at 15 kilometers per hour as seen from the other car. Now, the acceleration result. This is the big one. Let's think about what happens to acceleration when you change reference frames. Acceleration is the rate of change of velocity. So if I'm moving at a constant velocity relative to you, say I'm the train, moving at 20 meters per second to the right, then any change in velocity that an object experiences is the same in both frames. Here's why. Say the ball on the train starts at rest and reaches 6 meters per second relative to the train in 2 seconds. Acceleration relative to train equals delta V over delta T equals 6 over 2 equals 3 meters per second squared. Now from the ground frame, the ball started at 20 meters per second, just the train's velocity, and ended at 26 meters per second, train velocity plus final ball velocity. Change in velocity equals 26 minus 20 equals 6 meters per second. Time, 2 seconds. Acceleration relative to ground equals 6 over 2 equals 3 meters per second squared. Same. Exactly the same. So the acceleration of any object is the same as measured from all inertial frames. Why does this work? Because when you switch between two inertial frames, that is, frames that move at constant velocity relative to each other, you add or subtract the same constant velocity offset from everything. When you calculate the change in velocity, that constant offset cancels out. The delta V is the same. The time is the same. So the acceleration is the same. And why does this matter? This is not just a mathematical curiosity. This result is the reason Newton's laws are universal. Newton's second law says net force equals mass times acceleration. F net equals ma. If acceleration is the same in all inertial frames, then Newton's second law makes the same prediction in every inertial frame. The forces, the masses, the accelerations, all consistent. Physics works the same way on a stationary train platform and on a smoothly moving train. This is why when you're on a plane flying at constant velocity at 900 kilometers per hour, you can drop your phone and it falls straight down, exactly as it would if the plane was sitting on the ground. You can't feel the motion of the plane in the physics of objects around you, as long as the velocity is constant. The moment the plane accelerates, you feel it. That's because acceleration is no longer zero and the frame is no longer inertial.